Okay, so thank you very much for the invitation. So in this talk, I will discuss something which is in fact not related to classical transport or quantum transport, but for some transport, anomalous transport for some lattice gas with long jumps. So even if it is not directly related to this classical transport, I think that there are some issues which could be replied for this system, which could be of some interest for classical transport. So this is some joint work with several people and mainly from Portugal. Let me start with the initial motivation for this project. Okay, wait, what happened? Okay. So what is the motivation to this project? So as you know, during the last 20 years, there has been very fundamental progress in the understanding of non-equilibrium systems, which comes from what is called now the macroscopic fluctuation theory, which is some general framework to describe what are the non-equilibrium stationary state of a diffusive system. So when you are at equilibrium, for example, here, if you take some system like this one, a system in contact with some thermal bath, if the temperature of the thermal bath are the same, then we know that the equilibrium state of the system is described by the Gibbs formalism. But as soon as you change the temperatures are different, then the non-equilibrium stationary state in which you have some flux of energy or of particles between the reservoirs is usually not explicit. You cannot rely on some formula like the Gibbs ensemble. And so the macroscopic fluctuation theory, I will describe a bit later in more precisely what it is so has been developed mainly by Derrida and the group of Bertini and Alberto Sole, Davide Gabrielli, Gianna Zinio, and Claudio Landin, and many others since then. Since if you look on Google, you find more than 2 billion of entries just by typing macroscopic fluctuation theory, say that, in fact, if you want to have some understanding of the non-equilibrium stationary state of diffusive system in contact with some reservoirs, there is, by using some large deviation theory and hydrodynamic limit theory, you can have some definition of what is the non-equilibrium free energy. So I will be more precise a bit later. And so the motivation is the following. This macroscopic fluctuation theory has been developed for diffusive systems, so system in which in the bulk, the diffusion of energy or of particles is described by some diffusion equation. Now, the question is, what happens? Can you develop some similar theory in the case where you have superdiffusion? So for me, superdiffusion means something very precise. It means that the transport is described macroscopically by some fractional Laplacian. Instead of to have the Laplacian, you have some fractional Laplacian fractional equation in space. And so this motivates the things that I will present now in this talk, even if I will not develop, I still not able to develop a macroscopic fluctuation theory for superdiffusive system, but it is a long-term project. To be more precise about the systems that I will describe, let me give the example of the lattice gas I will be interested in, which is in fact some very well-known system, exclusion process, but exclusion process on the lattice in contact with some reservoirs, as you can see on the picture here, but in which, so exclusion process, that means that you have the lattice, and on each side of the lattice, you have only one particle or zero particle. So this is the exclusion rule. You cannot have more than one particle on each side, and it gives some interaction between particles. And now what are doing particles? They are acting as random walks, independent random walks, but with the interaction which is given by the exclusion rule. And so what is different from the usual exclusion process is that here I will consider the case where the probability distribution of the jump P is in fact a heavy tail. So it is in the form, so some constant in order to make it as a probability divided by the length of the jump over 1 plus gamma. And typically gamma will be smaller than 2. Smaller than 2, what does it mean? It means that if you compute the variance of P, then it is infinite. Okay, gamma less than 2 means that the variance is infinite. And in this case, if you know a little bit the exclusion process, you know that you understand that you will not have normal diffusion, because in the usual case, the diffusion will be proportional to the variance of P. And now we put the system in contact with some reservoirs, which will fix the density on the left to be rho L, and the density on the right of the reservoir would be rho R. And okay, so since you have long jumps, in fact, a particle which is in the bulk, so the bulk is this lattice of size n, a particle a priori could jump outside of the bulk. And so a model of reservoirs that I will consider is that here this blue part the infinite lattice, I consider the infinite lattice, and this blue part acts as a reservoir in which each particle can jump to this reservoir, and here you don't have the exclusion rule. And on the other hand, there are some infinite number of particles on each side, so some particle can enter in the system, but everywhere in the system. And this is a model of reservoir, and later I will discuss some reservoir which is maybe more natural for you, which is a reservoir which is acting only at the boundary on the nearest neighbor site. But it is a kind of reservoir that I will consider. And there will be some parameters which are which will appear in this model, which is the intensity of the reservoirs, which is regulated, in fact, by kappa, which is just a constant, positive constant, and theta. So theta can be negative or can be positive. So if theta is very, very positive, it means that the reservoirs are very weak. They don't inject and remove particles with a lot of intensity. If theta is 0, then it means that it is just for the one. And if theta is strictly negative, it means that the reservoirs are very active. They are injecting or removing particles with a very high intensity. And so I will denote, so we have some Markov process here with state space, which is given by 0, 1 per lambda n, okay, because the reservoirs are outside of the system, they are just reservoirs. And so eta tx is equal to 0 if the site x is empty, and eta tx is equal to 1 if the site is occupied. Okay, so I think that everybody here knows the exclusion process, and just the difference is that we have now long jumps, and the jumps can be very heavy-tailed so that you don't have any, you don't have the variance of P, which is finite. And so in this case, what you have is that you have some non-equivalent. Yes.
So yes. Yeah. So in the bulk, like particles can't overtake.
Can jump outside of the bulk, you mean?
Yeah, I mean, if J is say greater than, I mean,
N?
Greater than, say, like in the diagram, if it is greater than 5 or 6, then I mean, can it cross the two particles in the left?
Yeah. Yes. This particle here, you can
in the bulk. Let's say the particle in the 10, can it go to 1?
10 can go, yes, can go to 1, yes, with this probability.
Okay, thank you.
Which is P of 9. So, yes. So they can overlap. Yes.
Yes, they can fly over.
It is with the exclusion rule only. What was your question, Carlos?
Yes, if instead the particle flies over the reservoirs, then it is absorbed with probability 1.
Yes, here it is like if you have some infinite number of particles, so you can add some particle on each side. It is not a problem.
Okay, so that's not controlled by theta, by this parameter, this activity parameter theta. Okay.
No, theta is just controlling the way that you are injecting and removing particles from the. You can, because here you see you can also make disappear some particle in the reservoir. You can inject particle, but you can also remove particles, but everywhere. So this is a model of reservoir, but I will present some other model of reservoir, which is maybe more natural for you, but it will not change so much, in fact, the results. So if a system, so if rho L is equal to rho R, if you have the same density of the reservoir, then the system is at equilibrium. You don't have a flux of energy, a flux of particle inside the dot, and you have some equilibrium stationary state with zero flux. But if the temperature, the density of the boundaries are different, then the stationary state is unknown, and the Bernardin product measure are not anymore invariant. So let me, for example, for this model, say what are the questions that we would like to answer in order to develop some, so this is a long-term project to develop some macroscopic fluctuation theory for this super diffusive system. So, so the quantity of interest is empirical density, which is just written here. So it is 1 divided by the size of the bulk for the n, and the sum over x, eta tx, delta function u minus x over n. So it gives you the profile, the macroscopic profile of on the macroscopic scale 0, 1. Okay. And typically the first question that you address is the following. It is called the hydrodynamic limit problems. In some suitable time scale, which depend, you will let n goes to infinity, and you look at the system in a long time scale, which is depend on n, Tn per a, so a has to be fixed, has to be determined. Then what is the form of the profile if you assume that initially your empirical density measure is close to some macroscopic profile rho 0, then in this time scale Tna, you expect that your empirical density profile will be close to some new macroscopic profile. And this new macroscopic profile will be the solution of some partial differential equation. So typically in the case where you have just a nearest neighbor exclusion process, so this problem is very easy to solve. And you say that if you start from rho 0, then in the diffusive time scale, Tn square, so a is equal to 2 in the nearest neighbor case. And the rho Tu is just a solution of the heat equation with some diffusion coefficient, which is given by the variance of the okay, in this case, nearest neighbor case, it is just 1, but otherwise it is a variance of P of the probability distribution that introduced before. And this is the first question that you could you want to answer before to develop some macroscopic fluctuation theory. Then you can also be interested in the hydrostatic limit problem. So that means that you consider the non-equilibrium stationary state of your system. So you let the time going to infinity, and you ask what is the profile of the density profile, macroscopic density profile, rho bar, which is macroscopic, as n goes to infinity. Can you characterize it? So in the usual case, nearest neighbor exclusion process, symmetric exclusion process, it is just a linear profile between the density on the left and the right. Some other question you are interested in is the fixed law problem. Can you characterize how behaves the current in the system? So if I denote Gx as a current on site X, so by rescaling this microscopic current by depending on n, so you want to study the thermodynamic limit of this current and show that it converges to some something depending on the hydrostatic profile. So typically in diffusive systems, the B, which is here, is equal to 1. Okay, because of the normalization that I choose. Okay, so this is the second question. And now the macroscopic fluctuation theory, which is the following, is the study of large deviations for in the NES for the profile of the density profile. So the question there, in fact, you can decompose this MFT problem in two different problems. The first, I think there is some question.
Yes. So what is the B in the previous slide? N to the power B.
Okay, the B is some critical, some exponent which depend on the model that you consider. If you think about for example, the symmetric exclusion process in contact with reservoirs, maybe some usual reservoir, the B is equal to 1. B equal to 1 corresponds to normal transport.
Okay. Thank you.
And if B is less than 1, then you have superdiffusive transport. And if B is equal to 0, correspond to the case where you have ballistic transport.
Okay.
And so in the macroscopic fluctuation theory, you have two distinct parts in order to develop it. The first part is what I call the dynamical large deviations problem. So it means that you know that in some suitable time scale, your profile is the typical profile is given by what I called previously rho TU, which is the solution of some PDEs to determine. Usually in the classical case, in diffusive system, just some diffusion equation with some boundary conditions. And then you ask, what is the probability that my empirical density in this time scale, long time scale, is close to some other profile? And this probability will be exponentially small in the system size, in the thermodynamic limit. And you have to determine what is this rate in the exponential smallness. And of course, this function I, which is function I, will depend on the path. Okay, you are asking what is the probability to see a different path in some time window, Tt prime, of my empirical density. And of course, it will vanish. It will vanish on the hydrodynamic equation, which is a typical profile that you observe in the system. Yes, there is some question. No, maybe not. Okay. So this is the first step, and then there is also some other large deviation problems, which is in fact the way to define what is non-equilibrium free energy, which is the same problem, but now you don't ask about the large deviation for the path. You ask the large deviation for the profile in the non-equilibrium stationary state. So you start your system in the non-equilibrium stationary state, and in the non-equilibrium stationary state, the typical profile is a hydrostatic profile rho bar, and you ask what is the probability to observe some other profile, macroscopic profile of the density pi, and then again you have some, it will be exponentially small in the size of system n with some rate function f of pi. We depend on the profile pi that you want to observe, some large fluctuation. And the macroscopic fluctuation theory say that usually you cannot compute because you don't know what is a non-equilibrium stationary state. You don't have some formula. So this f of pi is usually completely impossible to determine directly from the non-equilibrium stationary state. And because you don't know it, it was some tour de force by Derrida, Leibovitz, and Speer to compute it for the exclusion process, for the symmetric and asymmetric exclusion process by using this matrix and sats. They were able to compute this f of pi, but usually when you consider some other system, it is almost impossible to determine it directly. While here, to determine this rate function, it exists some robust methods which are available for generic models. And so in order to compute this non-equilibrium free energy, what the macroscopic fluctuation theory proposed is to solve some variational problem, which is written here, which is if you want to compute this non-equilibrium free energy F, you can solve it by saying that it is the infimum over all the path, macroscopic path, of the large deviation functional rate, I, on the time window -∞0, when initially at -∞ you start with the hydrostatic profile, so the typical profile in the NES, and at time 0 you want to observe the large fluctuation profile pi. And if you solve this problem, this variational problem, which is complicated variational problem, but anyway it is something, then you can compute the free energy. So in this sense, it is some quite robust method because, as I said, these things usually you can derive them from there are some generic method to derive this rate functional for generic model, for example, for lattice gases, and then you can expect to compute the free energy in this way. So this is a motivation which has been developed essentially for the diffusive system with many improvements in many directions. But the question, so the long-term project is to develop some equivalent theory in the case of system which are super diffusive, in which the typical profile, the typical hydrodynamic equations are not given by some diffusion equation, but by some fractional diffusion equation. So I will not reply, in fact, to this problem here. We are still far from saying something interesting about it, but I will discuss the first part in this program. So the first model I will be interested in is the boundary-driven long-jump symmetric exclusion process. So that I recall here. So here you remember you have some long jumps, which are P of Z is of order 1 divided by Z power 1 plus gamma, and you have the action of the reservoir, which are regulated by kappa divided by N power theta. And so the first result that we obtain is about hydrodynamic limits. Hydrodynamic limits of this system. Okay, so I summarized in this graph. I didn't want to write as a precise statement because it is a bit complicated. But so what we can prove is that for this system with these reservoirs, the hydrodynamic profile is given by some equation, partial differential equation, plus some boundary conditions. So I will describe a bit later what are exactly these, the form of these hydrodynamic equations, but let me just give you some general picture of the result that we have. So the D, the operator D, which is here, typically for gamma bigger than 2. So gamma bigger than 2 means the variance of the jump rates is finite. Okay, so it is not very different from the nearest neighbor case. And this operator D, in this case, will be mainly the Laplacian, with some boundary conditions. While if D is if gamma is less than 2, then the D will be non-local operator and will be given by some fractional Laplacian. So there is a big transition between the case finite variance, gamma bigger than 2, and infinite variance, gamma less than 2. So let me first comment about the case gamma bigger than 2. Here you have two axes. Here you have the intensity of theta, okay, and here you have the gamma. So here there is a transition for gamma equal to 2, and the theta. So if you remember that the intensity of the reservoirs is inverse proportionally to n power theta, it means that when theta is big, the intensity of the reservoirs is very weak, while when theta is very negative, the intensity of the reservoirs is very large. So let me start with the case here, gamma bigger than 2, which correspond exactly to the case where you have just finite variance. So it is equivalent to the case where you have just nearest neighbor exclusion process. So as you can imagine, if theta is very large, what you will get in this case is some diffusion equation. But what would be the boundary condition? Since theta large means that the intensity of the reservoir is very weak, it means that you will not see the reservoirs. So you have like free boundary conditions. So Neumann boundary conditions in order to conserve the mass which is inside the system. So it is very natural to expect that you have some Neumann boundary condition if theta is very large, while if theta is reasonable, say theta equals 0, then the reservoir has some normal intensity and you expect to have Dirichlet boundary condition. And going from by increasing theta, you will have some transition that is given by for theta equal to 1, when the intensity of the reservoirs is exactly 1 over n, we have some transition in which the hydrodynamic limit change in the sense that you have still the Laplacian, dt rho t is equal to Laplacian of rho t, but the boundary conditions are now given by what we call the Robin boundary condition. So for people we don't know what are Robin boundary condition, it is something interpolating between Dirichlet boundary condition, Neumann boundary condition, and we say that the density of say at 0 is proportional to the flux of at 0. And so it's something which is interpolating between the two regimes. Okay, there is also some regime where theta is very negative, in which you have some reaction diffusion and Dirichlet boundary condition here, and here just some reaction term. And this reaction term, in fact, it is due to the fact that I have some reservoirs which are injecting particles everywhere in the bulk. So if theta is very negative, it means that the reservoirs are very strong. They are injecting a lot of particles inside the system. And so that, in fact, you don't see the motion of particles in the bulk, you just see the effect of the reservoirs. So in some sense, this regime is not very interesting. Okay, it's just the action of the reservoirs. So it is for the case where gamma is bigger than 2. So it is something quite well known. But now in the case where gamma is less than 2, it is much more complicated, in fact, because you have now the variance which is infinite. So you can expect that you have some fractional diffusion inside. So that is very easy to understand. But you have to impose some boundary conditions. And the boundary conditions are not trivial. Because why it is not trivial? Because a boundary condition is something local in some sense. Okay, you want to impose, for example, the density at the boundaries. But when you have some fractional diffusion, you have some non-local operator. And so the boundary condition cannot be something so local, in fact. So in order to understand, it is a bit complicated, in fact. And we observe that, so we describe a bit more precisely what are the equations that we obtain, but we obtain again some diagram like that, where instead, before we have this line with a Robin boundary condition, which was separating the two regimes here, we have some fractional diffusion and Robin boundary condition, which separate between some fractional diffusion with Dirichlet boundary condition and some fractional diffusion with Neumann boundary condition. And this regime is given exactly for the intensity of the reservoir, which is equal to gamma minus 1. So you can ignore a bit this red part, which is just due to the fact of the form of the reservoirs. And so I will describe more precisely what are these equations on this line, just to have some idea of what we have. Let me just comment about the fact that maybe you don't like so much my reservoirs. And so let me show you that if you use normal reservoirs in some sense, so I just use some reservoirs which are acting on one side. So you inject particle, but just on the nearest neighbor side. Okay, with some intensity, which is rho L, and here 1 minus rho R, you can make disappear particle. And now you forbid the particle to jump outside of the bulk. Okay, so it is a model a little bit different from the previous one, but in fact, the microscopic picture is not very different. The only fact we change respect to the previous picture, so the line of transition is the same, the equations are the same, just the this region, which was here, this reaction region, which was due to the fact that the reservoir were injecting particles everywhere in the bulk, is disappearing. But the rest is similar. So if you wish, you can think to this model if it is more natural for you. But in fact, the reservoirs, the model of reservoirs is not so natural. In fact, there is not just one choice possible. It will not change the general macroscopic picture. So this is the theorem that we obtain, and now I would like to describe a bit more what are these kind of equations that you can obtain on the hydrodynamic limits. Yeah, just before I just present some numerical simulation about here it is a numerical simulation of hydrostatic profiles, but in fact, if you make some numerical simulation for the hydrodynamic profile, you observe something very similar. So you can ignore a bit this pink line, but just observe the other line, which correspond almost all of them correspond to some gamma, which is less than 2. So in the case where you have some fractional diffusion, so you observe that these profiles are non-linear, even if the hydrodynamic equation will be linear. They are non-linear, and there's something which is interesting is that, in fact, at the boundaries, you have some kind of singularity in which here you see they are not differentiable. At the boundary, you have the tangent line, which is infinite. And in fact, there is some questions that I don't know how to reply even heuristically, which is how to characterize this behavior at the boundary. Can you compute, can you give the exponent, so the description of the hydrostatic profile or hydrodynamic limit profile at the boundary? This is something that I don't know how to solve. And now I would like to, so I show you this thing because I will come back later a bit about this phenomena. Let me present now the hydrodynamic limit. Yes, sorry. Before to present the hydrodynamic limit, I will just say that we can also observe some fractional fixed law, we call it fractional fixed law. It means that here you have some superdiffusive behavior. So it means that for gamma between 1 and 2, so I just present the result for theta equals 0, but we have also a result for any theta. So here you have some fractional, you have some superdiffusive behavior. And so it means that here it is a question before, the B is equal to gamma minus 1. So gamma minus 1 is strictly less than 1. And so the fact that it's strictly less than 1 is means that you have some superdiffusion. And we have some explicit formula. But as you see, so in the usual case, diffusive case, this current is just given by the gradient, mainly the gradient of rho bar. And here, as you see, it is a non-local thing, is a non-local object, which depends on the hydrostatic profile rho bar everywhere in the system. So it is a non-local flux. Okay. And okay, now I say, okay, I want to describe the fractional, the hydrodynamic limit or the hydrostatic profile that I have in my system. And so you can think that it is very natural to have some fractional Laplacian view in view of the form of the system where you have some heavy tail jumps. But now you say, okay, it is some fractional Laplacian, and since I have some boundary condition, it is fractional Laplacian in some bounded domain. And what is a fractional Laplacian on the bounded domain? And the answer is that it is not something which is unique. In fact, in the literature, there are several fractional Laplacian which are proposed to restrict them on the boundary some bounded domain, but there is nothing which is in fact so natural. From my point of view, there are many different objects which have been proposed, and which one has to be chosen. So let me recall just briefly what is a fractional Laplacian. So it is a non-local operator, and which is in fact non-local in the sense that if you want to compute for a given function f, the value of the fractional Laplacian here acting the function f at u, you need to know the function f everywhere because it is the integral over r of f of v. So it is a non-local object. Okay, so equivalently in Fourier space, it is just given by this symbol where for the usual Laplacian, you have psi square. So here is psi power gamma. So, okay, this is a definition. So we have two different visions. It is local in the Fourier space and non-local in the physical space. And now if you want to define some fractional Laplacian in a bounded domain, then you have to restrict this formula. How to restrict it? So there are several propositions. So there is what is called the restricted fractional Laplacian. So what you do is that you just take your function f, which is now defined just on the bounded domain 0, 1, and you say I extend it into a function f tilde outside of 0, 1 by just 0. And I use the same formula as this one. It is in the literature, it is called the restricted fractional Laplacian, which has some advantages because many explicit formula can be done for this kind of operator. There is some other possibility, which is a regional fractional Laplacian, and this is this one, which will appear, in fact, in my hydrodynamic limits, which is defined in the following way. you just take this integral, which is here for the regional fractional, for the fractional Laplacian, and you restrict it to 0, 1. And it gives you what is called the regional fractional Laplacian. There are also some other possibilities, which are the spectral fractional Laplacian, in which you take a function f, and you say, okay, let me choose some orthonormal basis composed of eigenvector of the Laplacian with suitable boundary conditions. So, for example, Dirichlet boundary condition, Neumann boundary condition, Robin boundary condition. So it can be cosine, it can be sine, with cosine pi nx, sine pi nx, or something else. And then you just use exactly this, the equivalent of this definition, but now in this bounded domain, you decompose your function on this basis, and then you just take the suitable exponent of the Fourier coefficient. And it gives you some other definition of a fractional Laplacian on 0, 1. So, and probably it is not exhaustive. There are maybe some other way to define some fractional Laplacian in some bounded domain. So what I want to say just here, it is not so evident what will be as the fundamental object will appear in the atomic limits. And what I claim is that it is in fact this one. It is a regional fractional Laplacian. So let me now give you some insight about what are the atomic equations that I can obtain. So I give just the example where you have the transition line, where you have some Robin's boundary conditions. And in fact, this atomic profile, even if the equations are linear, they are not explicit. It is not like in the case of just a heat equation with Dirichlet or boundary Dirichlet or Robin of Neumann boundary condition, in which you have some explicit solution. In this case, you don't have explicit solution, and the only way to characterize what is the only way that I know to characterize what is the macroscopic profile is to use some weak formulation of the PDE, which define a rho t. So what I mean by that, I claim that the atomic profile is a function of time and space, which satisfies some integrability condition in order that I can define all the objects which will appear. And so you see, if you want, for example, to define the regional fraction, the fractional Laplacian applied to the function rho, you need some kind of regularity of the function, because you need that this integral is finite. So in order that since you have the singularity here and this gamma is less than 2, you need some regularity. But since you have seen in the previous picture that I show you about the profile, they are not regular at the boundary, they are not differentiable. So it is not so evident to define what is a regional fractional Laplacian applied to rho. It is impossible, in fact, because it is singular, too singular at the boundary. So you have to pass by some weak formulation to characterize this atomic profile. And what we can prove is that, in fact, the atomic profile is just the unique profile which solves this weak formulation of the PD. So here it is a weak formulation of the PD, which is formally obtained by integrating by parts the solution with respect to some test function, which is smooth and for which everything is well defined. So you see L of G. So L, I recall you, is the regional fractional Laplacian. So L of G, because the function G is sufficiently smooth, is well defined. But L of rho a priori is not well defined. So I cannot write, for example, dt rho is equal to L of rho. I cannot write it directly because, in fact, L of rho does not make any sense. So I have to integrate with respect to some test function in order to make sense. And here you have all the boundary conditions which are implemented in this thing. And so there is a mathematical statement to say that there is a unique profile which satisfies these two equations, and this is a profile, the atomic profile that you observed in the atomic limit. And the main difficulty in order to obtain this result is to understand what are the boundary conditions. In the bulk, it is clear what we have. Okay, it is this regional fractional Laplacian appears very naturally, but the boundary condition is not so clear from my point of view. And I have to say that I don't think that there exists some explicit solution of this quite linear problem. In fact, it is a linear problem. I don't think you can write it in some explicit way. Okay, So this is a statement. So we have the same equation for all the regimes, but I don't want to describe more. So there are some questions which is, okay, so I am a mathematician, so I derive these hadronic profiles in a very rigorous way with a lot of details, but it will be interesting to have some more physicist-friendly way to derive this equation to explain what are these profile. So I mean, this is some question for the audience. I think it could be interesting to do it in the physicist way. And as I said before, the hadronic profile are not smooth, and at the boundaries they are singular in the sense that they are not differentiable. And I don't know how to compute the critical exponent of the singular behavior of the profile at the boundaries even heuristically. Okay, so this is in my long-term project. It is the first step, and the work in progress now is to derive the dynamical large deviation for the empirical density. Now that we have the hadronic limits and we understand well what is happening, and then to develop some macroscopic fluctuation theory in the fractional context. Okay, here also I have some remark is that I develop everything in the context of a reversible system, reversible, I mean, in the bulk. The P is symmetric, but there is also an interesting question is what happens if the P is asymmetric? And in this case, you expect to have some fractional Burger's equation with some boundary condition, but it is, I don't work on this subject, but there is some paper of Theorem about that. Okay. Okay, some other remark that I think could be of interest for this audience, and which in fact was some motivation for this work, apart from the development of some macroscopic fluctuation theory for superdiffusive system. So as we have seen, for example, in the talk of KG, there is, if you consider the FPU chains, one-dimensional FPU chains, so this theory of what is called the nonlinear fluctuating hadronic theory of Albert and now developed by many other people, predicts that if you have some interaction potential in this FPU chain, which is even, then the hadronic limits and the fluctuations should be derived. It should be described by some fractional diffusion equations. Okay, this is not proof for a system. It is argued in different way, and the numerical simulation are quite convincing, but it is not proved. And so the rigorous proof, I think I am exhaustive here by citing these three papers, has been obtained only for harmonic chains. So harmonic chain is a very bad model for diffusion, but in which you superpose some energy momentum conservative bulk noise, which conserve energy and momentum, so that in fact you introduce some kind of anharmonicity in your system without destroying too many things. And in this case, you can apply this nonlinear fluctuating hadronic theory for the system, and it is consistent with this rigorous work that I present here, in which you can show them. But all this theory here and all this paper are just centered on systems which are at equilibrium. You just study the fluctuations of some initial non-equilibrium state. Sorry, you have some system at equilibrium, you put some extra energy somewhere, and you look at how it's spreading. Now you want also to consider the problem in the NES. In the case of system, you can take a finite system, you put it in contact with some thermal baths, and you would like to describe what are the hydrostatic profile, what are the hadronic limits, what are the large deviations associated to this non-equilibrium stationary state. And that is a very difficult problem. And so it has been studied since, I don't know, I don't see now, probably, yes, 2008, maybe it was the first paper, I don't know. It has been studied in some work by by Carlos, Stefano Lepri, Antonio Politi, probably Roberto Livi, also myself, Abhishek, and so on. And so in this case, what you can show is that, okay, it is not rigorous, but at least it is quite convincing. It is there is a lot of arguments to support this fact, is that you have so the system is, again, the hydrodynamic limit or the hydrostatic profiles are described by some solution of some fractional Laplacian equations with some boundary condition. But I have to insist on the fact that the fractional Laplacian, which appears in these studies, is not the same as the fractional Laplacian that appears in my in the context of the exclusion process. Here, it has more the flavor of some spectral fractional Laplacian. Okay, so maybe I have to come back here. I presented three kinds of fractional Laplacian in bounded domain. So in the context of the exclusion process and the models that presented, it is this one, the regional fractional Laplacian, which is obtained by restricting on 0, 1, the usual formula. While in this model of heat conduction, it is something which has this flavor, in which you have to decompose your function on some basis and take as a suitable exponent. And so it means that in some sense, I was expecting at the beginning that maybe this model of exclusion process could reproduce in some sense the behavior of FPU chains, even if they are very different. There is a lattice gas, there is some FPU chain. So in FPU chain means that you have local interaction. In the system that I described, you have long range interactions. So they are different, but in some sense, they have in the macroscopic behavior is given by some fractional Laplacian in both cases. So this would be quite a bit similar, but we see that if you introduce some boundary conditions, they are very different. In fact, you don't have the same operator which appears in the hydrodynamic limits. And I have to mention some interesting paper by Stefano Lepri and Antonio Politi, which we were considering a few years ago. They wanted to describe a bit what are the hydrostatic profile, temperature profiles that you observe in the nest of some FPU chains in contact with some reservoirs. And they observe that if you take some models, quite simple model of Levy walks, you take some Levy walks, non-interacting Levy walks, which are traveling in some bounded domain, and it can be reflected, absorbed, or emitted by the boundaries. And if you choose carefully the way to inject or to reflect the Levy walks by turning in suitable way these parameters, then you can reproduce temperature profiles which are very similar to the temperature profile that appear in the FPU chains. So in some sense, these models reproduce better these temperature profile that you can observe in these cases than the exclusion process. Even in the exclusion process, you have some more interactions. And so it is something that I don't really well understand why it is so good here. And I have to say that, okay, in these profiles that you observe for FPU chains and for this Levy-Walks model, you have a picture which is very similar to this picture, in which you have some singularity at the boundaries. So in both cases, you have some singularity in the boundaries. In the model of Stefano Lepri and Antonio Politi, they are able to compute what is the exponents here, but in terms of the reflection and the emitting rates. But in my case, I don't know how to compute them. So it gives some second motivation to this system. And okay, do I have still time? Yes, maybe I have some time to present some other results for some other model, which is the boundary-driven symmetric long-jump zero-range process. Which is also some lattice gas, which a priori is more difficult to study than the exclusion process, because then in the bulk you have more interactions. And so we expect the hydrodynamic limits are not just given by linear equations, but are given by some nonlinear fractional diffusion equation. But on the other hand, the non-equilibrium stationary state of the boundary-driven long jumps zero-range process is simpler than the NES of the boundary-driven long jumps exclusion process. So let's just me present briefly what is the zero-range process. I think that everybody knows. So you have again the bulk, you have some heavy tail probability transition, and now the thing is that on each side you can have some infinite every number of particles, so the particle can jump from one side to some other side, and with some rate which is given by, so if you want to jump from x to y, p x y g of k, where k is a number of particles on side x, and g is just some function from n to m, so that g0 is equal to 0, and that this partition function is finite, where the gk factorial is just gk times gk minus 1 times gk minus 2 and so on. And so the jump rate of particle x to y is just given by this function g of number of particles on side x multiplied by this probability transition, okay, which is heavy tail. And again, you can make some reservoirs at the boundaries, which can be local or non-local, and with density alpha and density beta. And you can regulate the strength of the reservoir. So in this case, for the atomic limits, it's more difficult, and for the moment we are not able to derive them rigorously, but for the hydrostatics and the properties of the nest, we can go further, because in fact, the nest of a system is simpler. In fact, the nest, the non-equilibrium stationary state of the boundary-driven long jumps zero-range process has a product form. So it is something which is well known for the nearest neighbor, but it has a product form. It means that, okay, if you want the stationary state, you want to compute the this quantity, how k1 particle on site 1, kn particle on site n, then it is just given by the product of these marginals with a marginal which is driven by some fugacity which is varying with the sides. Okay, so on each side you have a different marginal which is driven by this parameter, this phi nx. Okay, x is a side and phi n is some suitable function. And what is good in this case is, in fact, it is some simple remark, is that you can relate, in fact, this phi n is not explicit. It is a solution of some linear problem, but okay, it is a linear problem of size n times n, so it is not solvable explicitly. And so it is semi-explicit in some sense. It is product, but it is not explicit. And the useful remark is that phi n of x can be related, in fact, to the stationary state of the exclusion process. So it means that if you look at the exclusion process in its stationary state, the average number of the average occupation number in the exclusion process with long jumps is equal to the g of psi x in the stationary state. So here it is the same notation, but here it is the stationary state of the zero-range process. Here it is the stationary state of the exclusion process. So there is a relation between the exclusion process and the range process, but which is only valid in the case of the stationary state. And since we know, in fact, what is the hydrostatic profile of the exclusion process, we can deduce what is the hydrostatic profile of the boundary-driven zero-range process, and it's just given as a function of the hydrostatic profile of the exclusion process. So rho bar is the hydrostatic profile of the exclusion process with long jumps, and m bar is the hydrostatic profile of the zero-range process, and they are related by some function r, which is just given in terms of this function, partition function z, which is written here. And so it is not very difficult once you observe this fact. It is almost trivial to see it, at least heuristically. Mathematically, it is a bit more evolved, but not difficult. And so you can plot what are the profile, and again, you see that there is some singularity at the boundaries. Okay. But the advantage now is that since we have some product form, we can go further and just not look at the hydrostatic profile, but also at the non-equilibrium free energy. And this is the last thing that I wanted to present. So we have also some, since it is quite explicit, we have the way to compute the non-equilibrium free energy of the boundary-driven zero-origin process with Longchamp. And it is given by this formula here. So pi is, so you remember the non-equilibrium free energy is, it is the rate which appears in the, okay, it is written here. It is the rate which appears, you want to observe some profile, which is not typical for the density, which is pi. And you say it will be exponentially small in n. And the rate is given by this formula. Yes, where capital phi is the inverse function of r with r, which is this function determined from z. So it is completely explicit. Okay, and this this formula is completely local. It is some local free energy, as you can see. And if you think about the exclusion process, we don't expect that it will be local. Okay, even in the case of local interaction for the exclusion process, we know that non-equilibrium free energy is non-local, but in the rearrange process is local. But at least, okay, this is, I think it is one of the first model with super diffusive behavior for which we have some explicit and some formula for the non-equilibrium free energy. And so the next step would be to try to drive the hydrodynamic profile of the boundary-driven zero-range process with Longchamps, which is more complicated than in the case of the exclusion process, because in this case we will have nonlinear equations, and then try to compute this dynamical large deviation, and then try to show that indeed that the macroscopic friction theory is valid, that this non-equilibrium free energy can be recovered from the dynamical large deviation functional of the path by this variational problem. But still, this is just a work in progress. We still don't have this which is done. Okay, so it was my last slide. So I hope that, in fact, so the main message is that I would like to invite people to work on this kind of system. I think it is interesting to try to develop some macroscopic friction theory for super diffusive system. I think that it could give also some insight for the same problem, which is much more difficult, which is for macroscopic friction theory for FPU chains, for example. But there are several questions, even in the case of lattice gases, which are not so trivial. Okay, so I thank you for your attention, and I finish now.
Thank you very much, Cedric. Thank you. Do we have any question from the audience? Yes, Stefano, please.
Sorry, it's me again.
No, thank you.
Cedric, the difference between FPU and the model that you're dealing, the main difference, of course, is also the fact that you start with the genuine Levy flight, in the sense that the particles can move with arbitrarily large velocities, right?
Mm-hmm.
So one difference would be that in the FPU chain we have a Levy walk, so it's something that has a finite velocity, so the quasi-particles cannot propagate faster than the speed of sound. Yeah, but in this model of the exclusion process, for example, so the drift of the particle is finite. Yeah, but the single move, it occurs with infinite velocity, right? It can move. What you call the single move? I mean, with the single step, the single jump. No, a single jump, no, because it is 1 divided by z power 1 plus gamma.
So if gamma is between 1 and 2, the first moment of the P, which gives the drift, what is the drift of the particles, is finite.
Yeah,
For
but what I
gamma,
mean is that it's the same difference between a Levy flight and Levy walk, no?
yes.
In the Levy walk, you have a finite velocity.
Yes.
Do you expect that one could expect that macroscopic equations are different in this case?
Yes, so you see the macroscopic equations are different, but only at the boundary, from the boundaries point of view. If you just look at the system without any boundaries, they are the same. They are given by the fractional Laplacian. The atomic limits are given by the fractional Laplacian. So this effect that you mentioned, I agree that there is a difference between Levy flight and Levy walks. You see it only at the level of the boundaries. I mean, it is only due to the boundaries that you have some difference. Otherwise, if you forget completely the boundaries, they are both given by some fractional Laplacian.
So your idea is that the same fractional, the same operator with different boundary conditions.
Yes. Okay. But if you don't have boundary conditions, you have, in both cases, you have the fractional Laplacian.
Okay, okay. So the difference in the profiles should come from the boundary conditions. Okay.
Yes, exactly.
And can you confirm that there is no way to compute this singularity? That you call it
I don't know how to do. I tried, but I didn't succeed. But okay, I invite you to try.
No, I mean I'm not able at all, because I remember we discussed 10 years ago this problem where we just did simulations. So that's the only thing that we could do.
But I asked also to some mathematicians which are involved in this fractional Laplacian stuff, and they didn't know how to compute it. It's not simple, in fact.
Because the only result that I know is this paper by Rosso, Cardar, and others, in which they were able to compute the behavior of one eigenfunction close to the boundary.
But for which
for the fractional Laplacian.
But for which one?
I think they use different definitions. Probably it's what you call the restricted one.
Yes, yes. For the restricted one, yes, I know.
Yeah.
It is quite explicit. Even for the spectral, you have some comparison. Yeah, but for this one, which appears here, which is a regional, seems that it is there is no explicit form. Nothing is.
So you confirm that there is no mathematical proof of this singularity.
No. Okay. So I would be interested to have some understanding of what is the behavior of his profile at the boundaries.
No, I agree, because I think this is one of the characteristic signature of this anomalous transport problem. So something that is everywhere. Whenever you have this anomalous transport, you have to take particle systems. Carlos knows very well. You always have the singularities of the boundary. So I think it would be interesting to know in general what is the shape of the singularity.
Yeah. Yes. But do you have some ideas? What could be a model of Levy walks which could be interacting? So in your model, you have Levy walks. They are not interacting.
No, they are not interacting. No.
But if you want to do it interacting.
Not that I know. I mean, probably that there exists something, but.
Okay.
But numerically, you know more or less how these divergence at the boundaries are, no, Cedric?
Okay, me, I'm not so good in numerics, so I don't know, but probably yes, it can be done. I think it should be possible to understand it.
Nice. We have another question from Abhishek. Please, Abhishek.
Hi, Cedric.
Hi.
Yeah, so I had two questions. One is similar to what Stefano asked. I mean, so if even on the infinite domain, I mean, like whether no boundaries, like Levy walk, I mean, it would have a, like if I look at the propagator, it would have a finite, like it can extend up to a maximum finite distance, right? So while a Levy flight will have infinite tails. So, and one of course has a finite variance and one has an infinite variance, right? So even on the infinite line, there should be some difference between Levy flight and the Levy walk.
Maybe. So what I'm saying, so
like if I look at the mean square deviation of a Levy walk, that will have a finite variance, right? Which will give me some anomalous coefficient. But a Levy flight, of course, will have infinite variance.
Yes, but so for the Levy flights, I guess that you have some. So the macroscopic equation is given by some fractional Laplacian.
Right. Yeah.
So, which is, I think, yes, Levy flights are quite similar in some sense to this exclusion process with long jumps, but not Levy walks. They are not similar to Levy walks.
Right. Yeah.
But they are not the same because as soon as you introduce some boundaries, then you don't have the same macroscopic behavior, which is different. So.
Okay. Okay. So the other question was, I mean, in the case of heat conduction, like sometimes we see that for different boundary conditions, it becomes like for fixed boundaries, I mean, it's kind of easier than with other boundary conditions, right? So is it that it's still the same, it's still a spectral fractional Laplacian, but just difficult to solve, or is it possible that it's actually not?
In fact, yeah, I didn't see it is okay. So maybe Carlos or Stefano remember, or you, because we wrote for some paper about it. So, but I don't remember in our paper what are the boundary conditions that we put. I don't know if you remember. And
you did fix.
Fixed, right? Yeah, fixed was easy to do, but and then I think for free there are some problems, right?
Maybe yes. Now I don't remember. I didn't read before. Okay. Yes, probably if we didn't do it, probably it was some problem. Yes.
Okay. But do you think it's possible that that because of the boundary conditions, it can go change the kind of Laplacian equation can change from spectral to the other forms that you mentioned?
I think so. No, because in the hydrostatic profile, for free boundary condition and for fixed boundary conditions, they are not the same profiles. No.
Yeah.
Yeah. Okay.
So I think it is not the same data which
yeah.
appear.
Okay.
Should be different. Yes.
Right. Okay. Okay. Thanks.
Well, very nice. Do we have more questions? Okay. If not, well, thank you very much, Cedric, for the nice talk. It's been very interesting, and the program you have is quite nice and challenging. So let's send Cedric again and both speakers today. And thank you very much.